Okay, so I'm just introduce Mario Jurić, who's a professor at the University of Washington and director of the DiRAC Institute there. And there's an abstract sent out yesterday and last week in the email announcing this talk, but the title is Science Platforms Enabling Scalable Collaborative Research.
Yeah, is it okay if I start, Adam?
Yeah, absolutely.
Okay, yeah, thanks for that introduction. As Adam said, I'm Mario Jurić. I'm the director of the DiRAC Institute at UW, and I co-lead the data engineering group there. So what I'll tell you, what I'll talk about in this talk is about science platforms, and I see many faces here in the audience who know about this even more than I do. So I hope we have a nice, interesting discussion at the end. But I'll tell you about a little bit about where this comes from, what's the rationale, some of the things we've done at UW, and where I think it's going to go. So let's talk about kind of some of the drivers for the science platform thinking today. And that is really the data set or the data-driven revolution in astronomy. So we used to be traditionally a pretty data-starved science. Observations were few and far between. They were quite precious. But in recent years, driven primarily by advances in imaging technology and computing, we've started to accumulate data at an unprecedented rate. And those data have been placed into archives. And today there are data sets with petabytes of imaging and terabytes of catalogs. And for many science cases, really, you don't need new observations. You can go into the archive and write papers based on archival data. And here, this is shown for the Space Telescope for HST, just because I had that easily available, but you can write similar plot for virtually any archive today. So this here is a very oversimplified diagram that's trying to illustrate the typical analysis patterns we see today. We have the archives which store and curate the data sets for us, usually in combination of file system and database backends. And then the user, so this is me doing astronomy, this is you doing astronomy, accesses these through web front end, usually grabs subsets of data selected through queries, downloads those subsets, and then uses an analysis resource that's typically local to actually do analysis on the data and understand whether that is what they were expecting or not. And this is then a loop. So based on the results of analysis, you may go grab a different subset, download it, do analysis, and so on. So the issue with this in this decade is that data sets are becoming fairly large. So here's a quick description or a quick summary of what to expect from ZTF, which is already on the sky, and then LSST, which will be on the sky in about 2 years. And so now you don't have to worry about the details of the numbers, but look at the units here. It's billions of objects, it's trillions of observations, it's terabytes per night, it's petabytes throughout the year. And the issue with science at such scales is that even a very small subset of these data sets, even if I down select LSST down to 0.1% of the total data set, that is still large, right? 0.1% of LSST is still about a terabyte. And using typical internet connections, that can take anywhere from 1 to 10 days to download to one's machine in your office. So this makes exploratory data analysis with its many repeated queries and repeated reanalyses very, very difficult. And so in the age of data sets that are at this scales, this download analyze paradigm starts to break. So what is the solution to this? Well, the solution is kind of fairly obvious, which is the data sets are becoming large, but our code that we actually use to analyze them is not. I've actually done this experiment. I went back, found all of my old codes going all the way back to graduate schools, and I'm not talking here about tools that are used, but like really analysis codes that I wrote to do this particular project, and they're all roughly not larger than 50 kilobytes or so. Some maybe better than that and have larger codes, but this is typically the scale. So rather than downloading the data sets, what you can do in this kind of environment is bring the code to the data. And this is something that is definitely not new. This is something that we've known about for a while and have been doing for a while. But the question is, how does that influence the architecture of what you expose to the user and the architecture of ultimately the archives themselves? So one of the ways the archives might change, first of all, the question is like, why don't we do this already? And the reason why we don't do this already regularly for like every single piece of analysis is because this analysis resource, the computers on which the analysis is actually performed, are outside of the archive where the data is stored. So if you think about how you solve this, how you want to solve this, then the solution appears reasonably clear, which is take the analysis resource, put it into the archive, and then make sure that the web front end through which all of this is accessed is now much richer, so that you can actually upload the code, run analysis on the code, run analysis in the archive, and do the analysis in a way that's as easy and as user-friendly as you would on your laptop. And this is kind of the concept behind science platforms, to give the user this kind of rich web front end that enables them to upload their codes to where the data is and to run the codes to where the data are as easy as they would from their laptop. And then a lot of the discussion about science platforms is how do we build this part correctly, and then how do we make these things in the back end scale? So this is something that currently at the moment is becoming quite accepted and adopted. You have things like CyVerse at Hopkins that's really pioneered this type of work. There's a fantastic service at a NOIR lab called Data Lab that allows you to access all of their internal data sets, all of their holdings through Jupyter Notebook, to which you log on, and LSST or Rubin Observatory is certainly building up one of these platforms for LSST data. So I think this is where the community seems to be going, and this will definitely help us take advantage of large data sets in the years to come. So while I think this solves some of the immediate pressures, there are still some issues that remain with these kinds of architectures, and that's what I want to focus on next. So first of all, nearly all or most current science platform concepts assume dedicated on-premise end-user compute resources. And there are some consequences to this. You have to start now choosing, you have to now provide the resources that the user would otherwise have at their institution yourself. So that means you need a large upfront capital investment to actually buy the nodes on which to run all these Jupyter notebooks and to enable the user's analyses. The alternative to that is you don't invest a lot into computing, but then you have to reduce the allocations. So then you get small per user allocations, and some of the early work we've done when we were sizing this for LSST, we found that we could afford about kind of one server per user, so an order of 10 to 20 cores per user, an order of a terabyte of data per user, and that becomes unsatisfactory. That introduces yet another bottleneck, because now the user's computing is next to the data, but they don't have enough of computing, and then they have to limit themselves to a small subset of a data set, again, that will fit into that computational allocation. And yet, as we think about some of the most challenging science with these large data sets, some of the most interesting science actually requires whole data sets. You want to crawl through an entire data set to find interesting objects, to look at statistical signatures, and so on. So we solved one problem, we've introduced another one. The other issue with just buying a whole lot of computing and sticking them next to the data in present-day archives is, what are you going to buy and how frequently is it going to change? We're typically going to look for some common denominator. You might end up buying a set of nodes, perhaps with GPUs that are perhaps some with GPUs that are current as of today. But 3 or 4 years from now, is that going to be what your users expect? Now, let's look at GPUs. If we're buying machines maybe 4 or 5 years ago, GPUs were still this a relative curiosity, if you will. There are certain areas where they were definitely effective, but the AI revolution hasn't hit entirely. That whole period where AI became really important happened in a very, very short period of time. So if you realize in 2 years that you need an AI accelerator, you can't really do much about it, right? Because what you have in the data set is what you have. So that's another problem, that these kinds of facilities tend to evolve relatively slowly relative to what's available elsewhere. Another issue you have is the data continues to be stored in traditional relational database solutions, and that makes it quite challenging to write code for parallel analysis. If you want to run something that's going to process in parallel a result of a query on all of LSST, you basically have to build in your analysis code into the query as a user-defined function or something similar. And that is something that requires significant skill. Our typical user will not know how to do this. And then I think the biggest concern I have about where things are going right now is that we're not going to have, I usually talk about this with my LSST hat on, but Rubin is not going to be the one big observatory out there in the 2020s. LSST is not going to be the only large data sets. There are going to be many of them. And where things seem to be going is that these major large-scale projects are going into different archives, and there's a danger that they remain geographically isolated. Yet the science would really benefit from cross-correlating a lot of these data sets. And so to kind of drive this point home, to illustrate the issue, here's a map of locations of data centers that are planned to house our key large astronomical data sets of this decade. And they're literally thousands of miles apart. So performing a joint analysis of, let's say, the LSST data and Euclid and W first requires changing them to a single location, which means downloading terabytes and petabytes of data. And the skills and resources required in such effort will effectively make it inaccessible to a typical researcher or research group. So such science right now would remain the domain of large national level projects, and mostly because of the cyber infrastructure challenge, not because of the challenge of the algorithms for the analysis. So what to do about it? One of the options would be to take all these facilities that are being prepared and then you consolidate them into one huge national astronomical data center, where you put massive amounts of compute capacity. You place, you create one rich web front end, one science platform, then everything is in one place, everything accessible. There's one-stop shop where a user can go and do their science. Now, this is not impossible. I think it's something that's within the realm of possibility, but I would argue against it. And I think there are a couple of difficulties here. I think building this up would require a lot of time. It would require significant upfront investment. That's challenging, even in the best of time, especially in today's fiscal environment. The consolidation to a single entity, I think, also brings elements of programmatic risk. Everyone will depend on this one facility. Any design or execution issues would impact the entire community. Another risk is that a consolidated center over time usually it doesn't have to happen, but it can become less agile than what you would do if you had some element of competition in there. And it's not, I think centralizing things in general is not ideal if you can avoid it. It's very difficult also to centralize expertise. So where I'm going with this is I want to offer an alternative, a different solution where we go ahead and try to leverage hundreds of billions of dollars of investment in cloud computing and in big data analysis system. So what I was talking about in the previous slide was essentially common infrastructure. And what I'm going to argue is that the cloud is effectively what already gives us that common infrastructure that has been built up and that we can use, that we can rent on an as-need basis. So the idea here is to achieve effective data set co-location by shifting them into the same or set of data lakes in the cloud. And this is something that will be possible almost immediately, and it doesn't require the construction of any additional hardware infrastructure. So rather, this kind of thing leverages existing storage infrastructure that Amazon and Microsoft and Google and others give you. That infrastructure is performant. It's almost infinitely scalable relative to what others are running on the cloud. Our data problems are currently relatively small, which is fantastic. It also makes use of the efficiencies and economies of scale that large cloud providers can realize, which is difficult for us who are smaller. The advantage of this is that once in the cloud, the data become effectively co-located with nearly inexhaustible pool of computing next to them. And so rather than being, and the other detail is that rather than being paid up front, sorry, is there a question? Oh, I'm hearing an echo, my apologies. So rather than paying up front for those resources, which cause significant capital expenditures, the capacity can be leased based on scientist demand. And this computing is varied. It ranges from traditional CPUs to GPUs to dedicated AI processors. It keeps getting upgraded all the time. Just a couple of months ago, I don't think this is relevant for us, but Microsoft added a quantum computer to their cloud, right? So as new technologies become available, they become accessible to us almost immediately. So there's a lot of attraction from that point of view. The other thing that you can do is then you can immediately also adopt industry standard big data analysis tools. There has been massive work over the last couple of years in the industry to solve exactly the kinds of problems that we were worried about. Cross-correlating different data sets, running through petabytes of data to find anomalies or to compute statistical signatures in matters of hours or minutes. All of this already exists, and we could be able to leverage it. The other thing that I think is interesting here is that this lets science platforms, this lets us build user interfaces that access these kinds of data sets, not just one, but multiple, by different people, by different groups. So, and all of those user interfaces, all of those science platforms, and here just as an example, I drew the existing ones that are already out there. They would have access not only to their own data, but to everybody else's data. So this has an advantage that, for example, I could be able to go to the LSST science platform or Rubin science platform and easily run a query that combines, say, LSST data with data from Euclid, even though perhaps the Euclid copy of the data has been maintained and kept in this lake by Ursa, whereas the LSST one has been kept by NAR Lab. And so these kinds of things make it introduce kind of an element of both complementarity and friendly competition between these platforms, because depending on what are the different offerings of each platform and what are the data set that you're interested in, you might want to choose to go to one or the other, or simply to port your research from one to the other. And the most, one of the more interesting details about this, or bits about this concept to me, is that once you have data sets located like this behind relatively standardized APIs, and really this is here we're talking mostly about S3 buckets. If I have an idea for a user interface for my specific project, or for an analysis interface for my specific project that's not addressed through any of the current offerings, right? Or if I have an idea for a service that I want to offer that runs on top of all these data sets, assuming I have the funding to do it, I can just go ahead and do it, right? Today, if I want to offer a different service, a new service that will run on LSST, I have to go through a number of different layers in the LSST project hierarchy to see whether there's a way for me to get the project to adopt the service to run in the data center. And the data centers are going to be quite understandably conservative about what they allow. With something like this, the answer is basically, if you can fund it, you can go and try to build it. And so this is an aspect that I really like, because it will enable us to build novel applications on these data sets with relatively little friction, limited only by funding and ideas. So this is a concept, and a number of people here in the audience have been talking about this for a while, and have been trying to build it in different parts and different ways. So we thought at UW, we thought we were going to give it a try with the main focus being enabling the use of the ZTF data set first to our researchers at UW, and then to researchers in the partnership and elsewhere. So we went ahead and tried to actually build a part of this concept that would have focused on ZTF, and then these two major data sets. There are a couple of others to enable our science and to illustrate how well this works. So a quick introduction to ZTF. ZTF stands for Zwicky Transient Facility. It just entered the second phase. Or the tagline is really a systematic exploration of the dynamic sky. So ZTF takes more than 1,000 images per night. There are hundreds of millions of detected sources per night. There are over 2 billion objects that are available in ZTF catalogs now, with roughly an order of 100 or more measurements per object per year. And there are on order of a couple 100,000 to a million alerts that go out per night. So our challenge here was to make this database of 2 billion objects, 2 billion time series, accessible to our researchers, and make it possible to easily cross-correlate, for example, ZTF to WISE, to SDSS, to Gaia, to other data sets. So we built up something like this. This is a quick architecture diagram. I'm not going to dwell on it much, but if you want to ask me questions about the details, please do later on. So the user is out here. All the access is through Jupyter. Everything is run on AWS. Our data sets are in S3. And then the Jupyter itself is managed using Kubernetes. The analysis, so kind of what you would think about as a database part, is done using something called Spark, which I'll talk about in the next slide. And then we discovered that users really need a shared file system to exchange their own notebooks, to exchange data, smaller data sets, and so on. So we wound up with this kind of analysis, with this kind of architecture. It's not to just have things in the cloud. It's not just sufficient to plop it into an S3 bucket and call it a day. You have to give the scientist a way to analyze these data sets. And so what we picked was a solution that's really common in the industry called Spark, Apache Spark. If you worked with Dask, you can think of Spark as kind of Dask's older and a little bit more mature brother. The thing with Spark is that it allows you to write quite easily understandable algorithms and pipelines in Python. So here's an example of one, and I'm not going to tell you what it does, but I bet that you can figure it out just by reading this Python code. It is extremely scalable. We've scaled it to, I believe, 128 instances. Then we actually, our data set was not large enough to go beyond that. Everything ended to finish too quickly. In industry, it's been scaled to more than 10,000 instances. And the really nice thing about it is it has full SQL support. So you're able to run in parallel queries that you were able to run, for example, on cast jobs on SDSS with very little modification. One thing we had to add to this is one thing that our science really demands is cross-matching objects in different catalogs. And this is something that's not available directly in these tools, industry standard tools out of the box. So what we added was a scalable positional cross-match operator. So you can do things like this, right? Take the GAIA catalog, take the SDSS catalog, and run cross-match. Basically join all objects that are within 2 arc seconds of each other. And then on the result of that, do some selection and some filtering and so on. And the way this is implemented actually all runs on the fly. So somebody uploads a third catalog, you can immediately run cross-match over it. There's no need to build cross-match tables or anything like that. So this made it possible to have data sets on AWS, on the cloud, and a scalable resource, and for the users to actually take advantage of that. Because when this query runs, for example, it can run an arbitrary number of machines and it can come back quickly. And the user doesn't have to worry about any of this. And if a machine fails, it'll get automatically restarted, and all of those details are handled for them. So here's a quick video of just basically this query that I just showed you how it runs. So this is an example of running with, in a Jupyter notebook, running with 32 instances of the cluster that does the processing. This is a trade-off of how quickly do you want to get your answer back. If the data set is big, you want to have a larger set of instances that work for you. Here is us collecting all the catalogs that are available in our data lake, actually running cross-match, and then running, this is a built-in function that we added to just plot a quick 2D histogram to get a feel for what things look like. And the thing that I really wanted to point you to is all of this this cross-match. So this is an on-the-fly cross-match, and then between GAIA, which is about 1.6 billion sources, and SDSS, which is about 600 million, it took about 3 minutes. This is, and then if we ran more filtering on that, it would essentially take roughly that same time because we're hitting some serialization bottlenecks. But the point is, it's fast enough, and it's pretty quick, and it hides all the complexity of the cloud. So this is just a quick demo of what this looks like. User doesn't have to install anything; everything is pre-installed for them. And our scientists really love this way of working. Just to show that we can do more than just simple demos, one of the bigger things we've done was to search for analogs of Boyajian stars in ZTF. So our time domain group searched for over 2 billion time series in ZTF to look for candidates that show dips like this in the light curve. And it was basically the technology or the cyber infrastructure element for them was essentially zero, and all of the work, all of the effort went into understanding how to write an optimal filter to find these kinds of dips, which is where you want to be in this kind of environment. And then to actually run this filter, which is written in Python, they simply spun up, asked Amazon to give them as many instances as honestly as we could pay for, and just run it. And the results come back in minutes or hours rather than days, which is our previous case with running this on-prem. So the nice thing, I think this illustrates the advantage of this concept, which is that we're a fairly small group at UW. We care about, we are in the process of building the LSST with our other colleagues, but really care about getting science out as soon as we can. And we're definitely not an archive or have no intention of becoming one. But we could build this on our own without much effort or without needing to coordinate with many different people, just as a prototype. And this is, to me, the beauty of this system, because you can grow something like this organically. If I at UW do something like this and put one of the data sets that we have access to in a cloud like this, and it turns out to be a good idea and to be a useful piece of science, somebody else might come along and add a different data set. So we're actually working with our colleagues at URSA who are experimenting with Access, with the Spark tool that I showed you, to add NeoWise to this combination. Some very early discussions with folks at MASC to see if we can do something similar with PanStars. And you can see this is the kind of thing where if you add more and more data sets, and everybody benefits, right? The moment a different data set is uploaded, it can be used from all of these sources, which is quite attractive. And so thinking about SCiMMA, because we want to have a research platform type offering, I think our natural contribution to this ecosystem would be a database of alerts and the alert streams themselves, right? And the benefit we get from this ecosystem is we can actually draw on all these databases that are in the cloud to add contextual information to our alerts. So this has been kind of a whirlwind tour through what we've done. This is my first part of the talk. And now I want to talk about something that I think is going to be on everybody's mind, which is how do we make these platforms, this all sounds great in theory, but how do we make them user-friendly and cost-effective? Because I bet that there's at least a few of you who want to ask me about how much all this costs. And the way I think about this is, winning the hearts and minds of users by making it user-friendly, and administrators by actually making it possible, cheap enough to run. So here I want to talk about Jupyter. Jupyter is the default science platform user interface, and it's nearly, there are others. There are some of you may have heard of Zeppelin, but it's not actually very much used in astronomy in our community. Jupyter is really the thing that people use and feel like this is the science platform with all the data sets behind it. So let me tackle the user-friendly question first. When users use Jupyter, what do they expect? They expect what I call a laptop experience, right? They started using Jupyter on the laptop. That's what they expect to see. This is based on running for about 3 years of our Jupyter offerings at UW and looking what our grads and postdocs and faculty do with it. Notebooks, first of all, notebooks are typically long-lived. I, as a user, when I start a notebook, I'm going to work in the morning. I expect to be able to go to lunch or take a weekend off without having to close my notebook or interrupt my work, right? That's kind of the basic requirement that everybody told us they expect. Expect to have access to my files, scripts from my notebooks. Expect to be able to utilize all available memory, everything that's available to me on my machine. And if I do run over, I expect the failure to be soft. So things are going to slow down, or Python is going to throw an out of memory exception. That's the kind of thing that people see on the laptops today. Expect to be able to utilize as much CPU as I can get. We've seen this on shared machines. Shared machines are nice, but people really prefer not to compete for CPU and memory with other users if they can avoid it, right? So this is why I'm thinking about this as a laptop experience. It's like running on your own laptop or on your own server. So if we look at Jupyter today, and typical implementation is running Jupyter Hub on Kubernetes, what are users actually given? So we usually deploy these things by either oversubscribing a large machine to conserve resources, or by allocating one host per user to achieve isolation predictability and increased cost. But that causes increased cost. So it's usually one of those two options. And depending on which one you choose, there are certain issues with this. So the first issue is users love to run notebooks for forever and ever. We've had some who have run notebooks for months. And if you leave it running for a month in the cloud, it costs a lot of money. So what the default is today is to terminate after about an hour. I think that is a default on Jupyter Hub or on Kubernetes on the 0 to Jupyter Hub setup. And that makes users very, very unhappy. The other issue is that in case you run out of memory, the way how Kubernetes handles containers that don't behave is typically they terminate them. It's an equivalent of killing the whole machine. And that is not user-friendly. Imagine if you ran a notebook for a day doing some analysis, you have 100 cells that you've processed, and then you make a mistake and you try to pull in a petabyte of data, and the RAM blows up. Instead of getting a simple Python notification that Python out of memory error, the whole thing may get terminated, and then again users aren't happy. And if resources are insufficient, then the users have to manually shut down the notebook and move to a larger machine, right? So that means that how's the user going to defend against that? They're going to want to start, no matter what they're doing, they're not going to start with the smallest machine, but they're going to start with a large machine because, you start small and then things grow larger. So why not? And that's a problem from the point of view of the operator because it costs money to run large machines. So platform operator's choice then becomes either poor resource utilization or poor user experience. And if you offer poor resource utilization, it costs you a lot. If you offer poor user experience, users will not come unless that's the only way to get the work done. And even worse, if the users do come, and if they feel that the user experience was poor, they're never going to come back, and they're going to go and they're going to tell their friends. And this has been studied a lot in history. There's a landmark study from 1965 that described this in song, and I think it's very applicable here. So treat the users nicely. Now, how do users actually use Jupyter? So we analyzed this, and while notebooks run for weeks on end, most of the time they're idle. We find that average research work utilization is on order of 10 to 20%. So that's about 3 to 7 hours per day. And in the meantime, there's lunches, there's group meetings, there are other things. It's minimal over the weekends. So this tells you there's a lot of room for resource management. If you can provide the user the illusion of a constantly running notebook, the ability to checkpoint it while it's not running, put it to disk, release the resources, and then restore it back when they come back, this could be a win-win for both the users and the operators, because the users then really have this illusion that their notebook has been running all the time, yet the operators are not paying for the full cost of that. And there really is a lot of room there because this number has been constant. We've been noticing this number to be the same, no matter whether it's our own researchers, whether it's postdocs, whether it's grads, whether it's schools that we helped run. So it really is at this level. So we realized, so this is something that Jupyter doesn't have, but we realized that it's possible to add, and then built a small prototype a couple of months ago that can freeze notebooks and checkpoint them to disk, and then restore them and also migrate them from machine to machine. And so this was for I think somewhat obvious reasons we named it ELSA. It also made my daughter care for what I work on for the first time in the last couple of years. And I'm going to show you a quick demo of how this works. And just to avoid any surprises, we're doing Zoom demos. I have it pre-recorded, so this will take you. I'll take you through this in over the next 5 minutes or so. All right, I'm going to show you a demo of our checkpoint restore functionality for science platforms based in Jupyter Hub. So here's our demo instance. Sign in with my Jupyter with my GitHub ID. And the first thing that I'm greeted by is our options as to which type of VM do I want to run. So let me pick the smallest one CPU, 1 GB of RAM, and hit start. So this will now spin up my Jupyter notebook container on the small instance. This usually takes about 10 seconds to spin it up. And after it's done, here's our typical, very familiar notebook interface. So let me open this notebook that I prepared for this demo, and the idea here is to demonstrate that I can checkpoint and restore a notebook and that it'll remember where it left off, so to speak, that this will be an actual checkpoint, not just shutting things down. So what I'm going to do are two things. One, I'm going to create a variable. I'm going to call it HW for Hello World. And then the other thing I'm going to do is I'm going to open a file, start reading it, and then halfway through I'm going to checkpoint this notebook. When I restore it, I'll continue reading this file, and you'll see that it'll continue where it left off. So it truly was a full checkpoint and full restore. So here's the contents of my file. It's called testfile.txt. This is a test file. It shows that open files are checkpointed correctly, and I'm going to open it in Python. I'm going to go ahead and read a couple lines. So this is and then I'm going to stop here. Okay, so now let me go and checkpoint this. I'll hit this green pause button, and what you're going to see is a progress bar showing that the checkpoint is in progress and asking us to wait a little. This usually takes about 20 seconds, and we know how to speed it up. I think this can actually take no more than, say, 3 or 4 seconds after a little bit more work. So we're done. And what just happened here is the entire container is shut down. All I'm seeing now is just the default page on Jupyter Hub. So my machine is not running anymore in the background. All right, so I'm going to go and start my server again, and it gives me the server options again. Just as before, I'm going to pick the small one, and I'm going to hit start. But what's going to happen now, rather than starting a completely new instance, is going to restore the checkpoint that it just saved. So what should happen once it goes back is you're going to see that this notebook is already running, or if I go up here, it's in the list of running notebooks. And if I click on it, I'll open up the notebook, and if I now go down here, my homework, my HW variable still has hello world. Note that in and out are at 7. And then I'm going to read a couple more lines. Note that we stopped at A. And the next line is test. Next line is file. Next line is white space. Next line is it. So there you go. It works. I round-tripped the whole notebook server on this instance. But I can do better than that. What I can do is, rather than round-tripping it to this instance, I can actually migrate it to a different instance. So if I push this button, what it does is it basically chains a checkpoint and restore, but in this case I can pick the instance at which I want it restored. So what I'm going to do is I'm going to ask it to restore it on a medium instance. So now we have to wait a little bit again for the checkpointing to occur. And again, this takes about 20 seconds in the current implementation. So here we go, a few more seconds. And now it's going to immediately start a server on the instance I've chosen, which is a larger one. The first one had about 1 gigabyte of RAM. This instance should have 2 gigabytes of RAM when it comes back on. All right, so here we are, we're back. Note that this is running. If I click on it, 2 things to note. One, this is now showing 1.8 gigs of RAM as available, so we have more memory. And 2, if I continue reading from this file, note that I was at it. Next line is shows, next line is that, next line is open, etc. So there you go. I can migrate from a smaller instance to a larger instance. Now, another thing I can do is I can actually go back. If my memory usage is such that I don't need a large instance, I can ask to migrate back to a small one. So I'm going to do that again. And again, I have now a little bit of waiting until as checkpointing happens. What's happening now is the contents of the memory are getting dumped and are getting sent across the network to storage. And right about here, it should be finished and started back on my small instance. And let's just make sure that it worked. Here we are. 800 megabytes, and I can continue reading the file here, and I'm done. All right, so this is there's also a second part of this demo which I'm going to skip in interest of time, where I actually show you that you can run much more complex pieces of code here. We ran the full LSST pipeline for shape measurement of galaxies, also checkpointed halfway through and migrated to a different machine. It just works. So this is kind of a quick summary of what the present system can do. It's fully multi-user, fully scalable, Jupyter Notebook deployment. Notebooks can be checkpointed to both the disks and migrated around. Checkpoint restore times, this is an interesting bit. They're already reasonable. I think 20 to 30 seconds is not terrible, but it is unpleasant. And they can get much better. I literally know with a couple of lines ago how to get this down to 2 or 3 seconds. The issue is that the current code actually tries to gzip compress all the memory dumps, which is completely unnecessary, and that the dumping takes 2 seconds and then zipping takes 18 seconds. So we have a pathway actually to get it down to sub-second, at which point you can make it completely transparent to the user. The user won't even know that the notebook migrated from point A to point B. At that point, you can also run notebooks on spot instances. There are some limitations. Right now, it doesn't preserve OpenTCP connections, which we actually know how to fix. So that the tools, the underlying libraries have that functionality. Just for fun, we ran a whole VNC server instance and tried to checkpoint it. That failed because there are some Linux APIs that this doesn't support, like iNotify. We don't really care about that in science work generally. Doesn't have support for HPC libraries, which I don't think there's an issue here, but there's no support for accelerators for GPUs, and this is something that there's work on adding that to the underlying libraries, but this is something that we would be looking at in the future to make better. So this is just a quick snapshot of what the high-level architecture looks like. This is very much a prototype, so we spun it up on DigitalOcean because it was fastest, but I think we can get this migrated to Amazon in about a couple of afternoons of work. So I'm not going to go in depth in technical details here, but I want to focus on how does this help. First of all, it gives you a huge user experience win because you don't need to terminate your users' resources, your users' Jupyter instances to conserve resources anymore. And then the second thing is, so this makes the experience kind of to users as if they were working on their laptops. But it's better than that because now the user can also migrate to larger machines as their workload expands. And so now you're getting in a place where you're not just trying to match the user's experience on their laptop, you're actually giving them something better. Because on my laptop, when I run out of cores, there's not much I can do. So from the point of view of the user, the machine's resources themselves become scalable. I can start working on 1 core and 2 gigabytes of RAM, and then I can scale up to 100 gigabytes and 60 cores if my work takes me there. And that's fantastic. That's really liberating from the point of view of work. And all of this can be done, this is my hypothesis at this point, is I haven't done it yet, but all this can be done automatically and transparently. So that the user won't even be aware of what's happening in the background. Their notebooks being shifted around. So this really gets us pretty close to the laptop field for science platforms. And I think it gets us beyond that. It becomes better than a laptop. And at this point, I think the users want to start making this their primary work environment. And we have kind of a simulated version of that in DiRAC, and virtually everybody, we don't have checkpoint restore, but we have one big machine where we run notebooks. Virtually nobody uses their laptops to run notebooks at this point. And the thing that prevented us from moving all of that into the cloud is cost, and now we're solving the cost with this. So that brings me to this slide. What are the potential cost savings? So if based on modeling of our typical users, so about 10 to 20%, we took 15% here as the duty cycle of their notebooks. That's depending on the instance you run on. And now note that with migration, you can actually run on spot instances as well, because when a spot instance is potentially terminated, you can move the entire notebook before the termination actually occurs. You can realize cost savings of factors of 10 to 20. And this is not theory. We've actually measured this and tried this out. So this is potentially fantastic. You're talking about giving the user a feel of working on an 8-core 32 gig of RAM machine, and it costs you on order of a couple $100 per year, which becomes comparable to running this on premise. So this slide, I don't have much time to talk about this, but let me give you a sense for our observed cost. So we have about 5 terabytes of data. These are heavily compressed. That's one of the things that the Sparks allows you to do. This is ZTF dataset, all the light curves, Gaia, SDSS, and then a couple of others. And that we're paying about $1,500 a year to keep that in S3. And note that you might say, well, for 5 terabytes I can buy a disk that's for $100 I can buy a 5 terabyte disk. But what S3 really buys you is scalability. You're not paying for storage. You're paying for the ability to access that storage essentially from an infinite number of instances. So we can go through 5 terabytes of data in minutes rather than in hours if they were sitting on a single disk. Pay about $1,000 per year and $700 per year for EBS. So these are disk volumes for users to share data. And the computing, this is more of an estimate because we've done so many different experiments. It was kind of difficult to disentangle, but we're guessing that for our group, which is about 20 people, computing will come out to $5,000 a year. And this part is probably the most variable of all. It really will depend on how the system is utilized. But it's becoming feasible. It's not incredibly expensive. We're not looking at $50,000 a year, which was surprising to me, to be honest. So to end this, what are some kind of based on what I wanted to show you here? I wanted to argue for looking at the cloud as we start setting up the next generation of science platforms, and because that allows us to share data much more easily. And I wanted to show you that there's a way to actually making this cost effective without sacrificing the user experience. And so where I think that this is all going in the future is this type of checkpoint restore and line migration support. This will improve a lot, and this will be integrated into Jupyter proper. This is something that we really want to do. For now, to get this demo running, we just have Jupyter in very unpleasant ways. The other big thing that I didn't talk about here is real-time shared editing of Jupyter notebooks. That is also being done. I think the team at Berkeley is funded to actually do that and put it into Jupyter notebooks. And then you have a combination of these two, which I think make it irresistible for a typical user to stop using notebooks on their laptops and actually use the offering that an archive or a cloud provider would give them. With these kinds of checkpoint restore capabilities, the cost of running typical analysis start becoming comparable to on-prem, but now they have much better user experience because you can do real-time shared editing with your friends. You can migrate from smaller instance to larger instance as you need, and so on. And plus, running in the cloud brings, if there's a critical mass of data sets that are in the cloud, this becomes irresistible to run that there, because I don't have to worry about which data set is where. I can just log on to my Jupyter notebook and run queries against all of them. And so where I predict this is going to go is, I think our users will soon prefer, if not demand, to work on remote instances. And whether they're cloud-based or not, I'm not 100% clear, because you can build a lot of this, for example, at a large data center. But I think the cloud-based version of this would really bring the biggest flexibility. And the last thing I want to leave you with is that I think this will happen much faster than we think. Think of transitions to webmail. Those of us who are old enough before Gmail and others ruled the world, we had email clients. Something more recent, Google Docs. Everybody uses Google Docs today. or even more recent, Overleaf, right? Overleaf sounded like this crazy thing that's going to go bankrupt because who was going to pay for web-based LaTeX editing? And yet now we all use it. And I think if someone took it away, we would be quite unhappy. And my feel is that this is where we're going with user analysis and notebooks and so on. So I'm going to stop here and thank you. And please let me know if you have any questions.
Thanks very much, Mario. There were 2 or 3 questions in the chat, and then we'll go to people by order of raised hands. And I apologize, we may run over. I think we're going to run over the hour a little bit, but this was really, really fascinating to watch. So the first question at 47 minutes past the hour was from Stephanie Juneau. Would you like to ask your question, Stephanie, or shall I read it out?
Sure, I can ask it. Hi, Mario. This is a very interesting talk, so thank you for giving it. I was curious when you were showing the demo with choosing a VM and running an instance of Jupyter, if the user saves and doesn't migrate to different size. So basically they have to remember which size to launch again to retrieve their previous work. What would happen if they pick a different size VM?
Oh, it will. So if they pick the larger VM, it will just work. If they pick one that's too small, it will refuse to run. So failures are non-destructive. That's a really nice feature here. So if for whatever reason migration fails, it'll leave things as they are.
Okay, with some kind of warning that the size was too small, or this is not yet ready?
Yeah, right now, I mean, this is like a very rough prototype, so we don't have that level of user friendliness, but like the technology is there to basically tell the user, look, this was too small for this reason. Yeah.
Okay, thank you.
Okay, cool. And then also in the chat, Phil Daly had asked, do you want to ask Phil, or shall I?
You can just read it out. It's more of a comment
Okay.
than a question, but if you need a clarification, I can do it.
Okay, is this a wheel reinvention? Is this the same sort of thing that CyVerse has been doing for a few years?
Which part?
The whole Jupyter UX integration, Jupyter Lab, Jupyter with instances.
Oh, I'm not, yeah, no. I mean, I'm not claiming that this is the first time anyone put a Jupyter hub in front of a data set. CyVerse, I think, as I mentioned, has definitely been a pioneer here, although they started with Jupyter, I think, relatively somewhat more recently. And Data Lab, I think, is the best example here with Jupyter as a front end. My point here is that if every single archive sets up one of these, and we still keep holding the data sets inside and don't have an easy way to share them and to access from one platform to access data sets more broadly than just what the holding of a certain archive center is, that I think we're missing out on a potential new application, new functionality here. That's really what I'm pointing to.
If I can, just real quick on the CyVerse portion, it's been done for a while, but I'm just going to say this checkpoint, restore, and migrate functionality. I'm writing an email right now to you, Mario, asking if we can check it out here at TAC. But I think that's a game changer in how this can work in a data lake environment.
Yeah, I was really excited when we realized that the technology is advanced enough that we can do it. Yeah.
But I think CyVerse does that, doesn't it?
No, they remain running in the Kubernetes cluster. They don't get checkpointed and restored or migrated. They just allow you to interact in a Jupyter environment with the storage systems and then submit jobs to the larger systems in the background. But
thanks for the details.
Cool. So then I think the order of questions in terms of hands up, I think it went David Kaplan, Newt Olson, and Robert Nikuta. And I apologize to anyone whose name I mispronounced. David,
thanks, Mario. Again, very interesting. You said at the beginning, we have the Jupyter set up. You don't have to install everything. Everything's already there. But of course, many new things are developed every day, and a lot of people do their own development and deployment. So is there an easy mechanism for, say, a user to either just within a single environment or for a number of users install custom Python packages or access, just compiled code that they need for their particular tasks?
Yeah, the short answer is yes, and the longer answer is where are you? This is part of the reason why all of our setups have a shared file system, because then you can install an environment for either you or your group without having to ask the administrator to do it globally. Yeah, that was like the #1 request that we got when the first instance of this went out. So the short answer is yes.
Great, thanks.
Okay, next hand up was Nick.
Hi, Mario. Thanks for that talk. It was really good, very compelling vision. Is there, what do you think about, this is all sort of based on avoiding large data transfers over the network, but of course, networks are also advancing in capacity. So 5G will, I think, isn't it like 10 gigabytes per second or something? That will be the jump in network capacity. Is there a danger that developments in network access speed sort of obviate some of the need to put everything into a cloud instance? I mean, I think that there's lots of other arguments for doing it this way, but that might be a counter argument.
Yeah, I don't believe so, at least not in the short term. To be honest, this kind of architecture, nothing prevents you from doing both, right? Like if the networks become fast enough, then everything here, most of the things we build talks to everything else by S3 APIs. So you can easily, keep your data sets at home, quote unquote, with a big pipe. I think that over the next 3 years, I'm kind of focused like, what are we going to do with LSST data in 3 years? And I think networks are not going to be, or things are not going to become fast enough in that time span. Yeah, I mean, if things change, 5 years from now, and networks, the bandwidths go up that much, nothing in this architecture that prevents us from making it a bit more distributed. Or vice versa. You can start distributed and then bring things together.
Okay. Thanks.
Okay, and last question is Robert.
Thanks. Hi, Mario. This is Robert. Great talk. So I have 2 questions, if I may. And I've seen your talk about ELSA at JupyterCon, so I will not ask the technical questions that I might also have, but rather about the first part of your talk. So one is, it strikes me that we're trying to, bring the notebook experience, laptop experience, and enable the user to do that, even if they move to new technologies, even if they move to much more complex analysis tools. And I was wondering what your thoughts are on maybe us investing significantly more resources in training the community in using new technologies and then developing, workflows and analyses that they never thought of possible, rather than, or in addition to us, simplifying and mapping new technology to old behaviors.
Yeah, no, absolutely. I think we have to meet somewhere in the middle. And the question to me is, what is your typical astronomer, how do they spend their time, right? If they spend most of their time actually writing some piece of code, then that is, and using a certain framework, then that framework can be relatively complex because it will always be fresh in their mind because that's what they do on a daily basis. Those kinds of things, I think, that they do on a daily basis, that's where we need to invest in education and bringing users up to speed. If there are things that users have to do, say, every month or every 2 months, right? If something goes wrong and then they have to understand what happened at a fairly deep level, but that happens every once or twice a year, users are not going to remember that, not going to remember how to do that. And telling them, oh, you need to learn to use this tool to diagnose it or something, do something more complex, right? That's not going to gain a lot of traction. So when I'm thinking about what needs to be simplified and what needs to be, and where the right answer is just tell the user to suck it up and learn how to use the right tool, I think if they're going to be using that tool on a daily basis, then I think it makes sense if it's going to make a big difference in their workload. But if it's something that's rare and that happens, that they do maybe once when they're setting up all of the data sets, and then for the next half a year while they're working on projects they don't, that has to be simplified for them rather than we tell them go learn everything about S3 APIs to work with this thing. So I don't have really a hard and fast answer for you for a particular for general technologies, but like if we start talking about the specific bits and pieces, then that's where I think we can make some informed decisions. So this is why I think it's good to keep the user to abstract away things like fault tolerance and resilience to failure and parallelizing over many thousands of cores, right? You want the user to think in terms of their algorithms. What do they want to do with the data set? How do they want to? You want to spend most of the time figuring out how to fit a light curve or whatnot, and not figuring out on dealing with at low level with some frameworks of parallelization, because that's not what we do as astronomers.
Okay, so I actually have plenty of questions of my own. I'm sorry, Robert. I have plenty of questions of my own, but I can ask them anytime. So we'll say the last question will go to Rick McMullen.
All right, thanks, Mario. This is a spectacular talk. Enjoyed many parts of it, and I think you're hitting on some very interesting issues. But underneath it all are our friendly administrators, and you make a compelling case that storage and computing are cheap in the cloud if you keep to certain rules and whatnot and do what you've done with ELSA. So the bigger question is, a part of the synergy that you proposed earlier was having all of these data sets available in the cloud, which is not a matter of 5 terabytes. So the question then is who's going to pay for it, and how are you going to get owners of that data to do that? Or are you just going to be shuttling data in and out depending on what project you're working on and what specific data you need to leverage this super available integrated cloud environment?
So I think this is something, I think you've hit the nail on the head. It's the data at rest that we have to keep in the cloud. How much is that going to cost, and how much will that cost relative to what we're paying for it to keep it on premise? The interesting bit that we found is not all data is equally valuable. LSST may be generating 6 petabytes of data per year, but actually only perhaps a few tens or hundreds of terabytes are going to be generating 99% of the scientific results. And that's why we just for our work we ended up utilizing, we thought that we were going to have 50 terabytes on S3, and it ended up being an order of 5, because it's the catalogs that bring most information. And even within the catalogs, there are kind of smaller subset of hot columns that really bring 99-point-something% of information. I think understanding, this is something that I think our archive colleagues will have really good insight into. Which are the columns that the users are hitting? What are the subsets that we make available to something like this to keep things to keep costs under control? And then for things that don't fit into that subset, how do we make that maybe slightly less conveniently available, but available? Here we keep everything at S3, but just Amazon has, I think, 4 different levels of storage with different access patterns and costs. So you may decide to keep all of LSST on Glacier and maybe pull it up once a year to do major reprocessings and things like that. But it's hypothesis. I'm speculating right now. But my only point is that we were able to do a lot of science with just 5 terabytes. A lot of diverse science, I should say.
Thanks. That's very helpful. I guess the NIH has got the gleam in their eye a couple of years ago, and it's not quite worked out the way they had been expecting for some not so obvious reasons. the main one I think is that their approach is to put an entire data set in the cloud and let it sit there, as opposed to a more nuanced approach of putting what people want in the cloud.
Well, I think that the flip, that's kind of how we started somewhat naively, and then nobody could use it. And then we turned our focus to, what is the tool we need to build on top of this for it to be actually usable? And that's how we came up with Axis. So if you give the users a combination of, here's a way to go through 2 billion light curves in 30 minutes, right? And do it in Python. So, and not to worry about scaling and so forth, because the framework does it for you. I think that was a big piece that we were missing, like the tool to actually make use of those data sets.
Okay, Mary, there's one question again from Stephanie. Regarding that real-time shared editing of notebooks, are you referring to Jupyter-RTC or some other effort?
To be honest, I'm referring to whatever Fernando Perez was referring when we spoke 2 weeks ago. I know that they're working on it, but it's not ready for prime time yet. I haven't seen it myself.
Okay, so thanks again, Mario. And within about 24 hours, this should be up on the SCiMMA YouTube channel. So you'll be able to go through it again. And perhaps if other things occur to you, you can follow up to questions to the Google group or to Mario. So thanks to everyone for attending. Sorry we overran a little bit, but this was really very, very interesting. I think this is, I'm wholly sold on this as the way forward rather than building more and more systems on-prem.
I think there's still some serious issues with cost that we have to figure out, but I think we're getting there. It's been an interesting ride over the last 3 years. All right, thanks everyone.
Thanks, Mario.